So this is chapter 52 out of your book they title Cranking System. I appreciate them terming this cranking system because that kind of is a good description of what the starting system on the car does. It's responsible for cranking the vehicle over. The fault that I find with defining this as cranking system is that it's not called the cranking system officially in the automotive industry. We would call it the starting system. And so if you went to service information or anything like that and you try to look up cranking system, you're not going to find anything because we refer to it as the starting system. And so this is chapter 52 that is about starting systems, which its job is to crank the vehicle over, the engine over. And so originally back in the day, before electric starters like you see in front of on the bench top here in front of me, people used to manually crank the engine over to get it started and get that crankshaft turning fast enough and the four-stroke cycle moving to where it could fire up and run on its own. Electric starters came into be where then we could start with an electric motor. What I have in front of me here is two of the common styles of starting systems. And so we have right here the Ford way of doing it and then everybody else. So Ford, everybody else. So, and even now Ford has come in line with everybody else. But some of your early Fords would have a starter motor like this and a separate starter relay. Then pretty much everybody else would have their starter motor and a solenoid. So this one is a solenoid, and the difference between a solenoid and a relay is a solenoid is an electromechanical device, so it has an electrical function and a mechanical function, and a relay is just an electrical device that it connects an electrical circuit. And so this is a high current relay. It carries a massive amount. It's got battery cables that would connect on either side. And then in the same way, the solenoid does as well. It has a terminal for massive cables there. But then this not only connects the high current side of this, the cable to the motor, it not only makes that connection for the starter motor, connecting that high current, big terminal cable to the starter motor, but then it also is responsible for kicking out the pinion into contact with the relay. So as it pulls in and makes contact electrically, it also moves the shaft out for the pinion to engage the pinion with the ring gear. So wanted to make that point about the two different designs of starting systems. Pretty much what you'll see for the most part nowadays is starter motors that would look like this one with a solenoid and then the motor itself. So the starter motor or starting system is going to use our battery power, our chemical energy stored in the battery to operate this electric starter motor to crank the engine over. Obviously, during cranking, to have an engine that will fire up and run, we have to have ignition system, fuel system, computer controls involved. But the starting system's primary purpose is crank the engine over. And so as you would imagine, when starters fail, we get the same symptom as when batteries fail. We have vehicles that don't crank over. So when we turn the key to the start position, then we'll have the small gear on this starter, which is the pinion, kick out into the large gear that is our ring gear that'll engage the back of either a flywheel or a flex plate. On an automatic transmission, we have a flex plate which bolts to the back of the crankshaft in between our engine and transmission, and that becomes the mounting point for this ring gear for the pinion on the starter to engage. And so on a manual transmission, it's called a flywheel, and that becomes the attaching point to transmit and connect and disconnect power from our engine to our manual transmission. A flywheel is a lot thicker and has a lot more mass of material that becomes a friction surface for our clutch. The flex plate not only is a mount for the ring gear for the starter, but then it also is the mounting point for the torque converter, which is what mechanically connects our automatic transmission to the engine. So then when the key's released back to the run position, then that pinion will disengage from that ring gear, and then the engine's will have fired up and is now running on its own, and we de-energize that starting system circuit. So the starter itself converts electrical energy into mechanical energy. So the electrical energy, we have the battery that has chemical energy, and it converts that chemical energy to electrical energy, and then that starter takes that electrical energy, converts it to mechanical energy. Then the engine takes the energy that's stored in fuel, converts that to heat, and that heat to mechanical energy. Mechanical energy drives the alternator, so the alternator converts mechanical energy into electrical energy that then goes back to the battery that takes that electrical energy and converts it back into chemical energy. And so the whole point in saying all of that is to illustrate the idea that energy is not created or destroyed, it only changes form. So it's really full circle in this case with the starting system, that we've got electrical to mechanical, then mechanical to electrical, and then electrical back to chemical, then the battery, chemical to electrical. And so it's the full circle that energy isn't created or destroyed, it only changes form. So the starter's needed to crank the engine over, it gets that crankshaft moving, and it starts our 4-stroke cycle off. The load on the starter is hardest on a cold start because the oil will be thicker. That thicker viscosity oil is harder to pump, it's harder to turn the crankshaft through, and so we have a higher cranking load on the engine when it's first started in the morning when it's cold. Ironically, when it's cold, it's also hardest for the battery to produce electrical energy, and so we have kind of a double whammy in that sense, that it is hardest on the starting system when it's cold versus when it's hot. So these are the components in our starting system. We've got our battery, ignition switch, cables and wires, our starter solenoid or relay, if it's our common starting system with a solenoid and a motor, or if it's the relay style with a Ford. So that's why it's either or. Then we've got our starter motor and then some sort of a safety switch as well. So we'll bring in some of this stuff. We break up our starting system into 2 circuits. So understand, when we say circuit, every circuit that we ever have has a power source, it has power and ground conductors, right? Power and ground, it has a load, right? So there's a control circuit that has its own, that has a power source, the conductors, and a load. And then there's a motor circuit that has power source, conductors, and a load. The control circuit controls the motor circuit. So the control circuit is controlled by the key, right? And I understand that a lot of newer cars are push to start, little push button starting, but the control circuit is our small gauge wires that's controlling the high current motor circuit. Motor circuit obviously then includes the starter motor itself. So the control circuit is using a small amount of current to control the high current motor circuit. And so it consists of our ignition switch, some sort of a safety switch so we can't start the car in gear or in drive, and then the starter solenoid or relay. The control circuit is often where we get our alarm systems installed, if it's a crappy alarm. So we'll kind of talk about that and where they install those. So our motor circuit supplies power to operate our starter motor itself. So this is the high current, big battery cables is all part of your starter motor circuit. Carries that current from the battery that leads to the starter motor. That would include your starter motor, again, your relay or your solenoid. So it's in both circuits, the battery, and then your large cables. So if we look at a basic starting system, this would be our control circuit. So power from the key comes to the relay, goes to ground, back to the battery. Then we've got the motor circuit, which is your battery cables here, that goes to the starter motor and then back to the battery. So what is the load in each one of these circuits? Because every circuit has a power source, which is our battery for both circuits. And then they've got our conductors and they've got the load. So I want you to think about what the load would be in the control circuit here, and then our motor circuit. So in the motor circuit, the load in the motor circuit is the starter motor. In the control circuit, the load is the relay or the solenoid. So In the load on the control circuit for our small gauge wire is our solenoid or our relay. The load for the motor circuit is the starter motor itself. Now, for most of your cheap aftermarket alarms, what ends up happening with these relays is they get power from the key, and this just connects this wire to this wire, and it continues power onto here. There's a winding inside here that creates a magnet that magnetically connects these two terminals together, and then we have our ground over here. Most of the time for alarm systems, what they do is they interrupt the small wire on the starter. So on here, if we look at this starter motor, then you can see there's really only two terminals on here. There's a power wire that would come from the battery here, and then there's a terminal right here for a small wire right there, which would come from the key. So the small wire from the key would go there. Then that when it's energized turns into a magnet, connects these two terminals, and then we get power down to the motor. The ground path is the housing of the starter to get back to the battery. So what they do is they interrupt power from the key. So you turn the key to start. If they make an open circuit there, then no power gets here. Obviously, I have power waiting right here, so if I jumped a screwdriver from there to there, I'm stealing power from this big terminal here to connect it to there, then you can get a battery to crank over, get an engine to crank over that way and operate the starter by getting power to the small wire. So, not too tricky there. So that would be our two wires there and two circuits. So the ignition switch, want to spend a little bit of time talking about the ignition switch. Ignition switches generally have these positions. They have an accessory position, an off position, an on position, and an on or run, and then you have start. And so older cars, when you first put the key in the ignition, it was in the off position. If you turned the key backwards, that would put you in accessory, where then your windows roll up and down, your radio comes on, stuff like that. But the major components that are necessary to get an engine to start up and run would not be energized in accessory. Then if you turned it back forward one from accessory, then you're back at off. One forward is detented, so if you took your finger or your hand off of it, it would stay there. And then we were spring loaded in the start position, to where if I turned it to start and I released the key, then it would spring load back and default to the run and stay there. A lot of your newer cars, when you first turn the key in the ignition, you're in off. You turn it forward one, your accessory. You turn it forward again, you're in run, and then it would spring load to start. On your push to start cars, if you have your fob with you and you press the button without your foot on the brake, that'll get you to accessory. If you put your foot on the brake and press the button again, then the computer takes over, starts the car, defaults back to run. And that would be your key position functionality. On a scan tool or in scan data, it would still represent these different positions on the scan data, even though the computer controlled it all. So, talk about our battery cables. Our battery cables are our power source for this vehicle. The battery is the power source for the vehicle, converts our chemical energy to electrical energy, produces a massive amount of current for a short period of time, which is perfect because that's what is necessary for the starter. The cables deliver that power to and from to the starter motor and back to the battery, and so that's what these large cables are all about. We have these big cables that we have electrical power that's coming in on our positive cable, going down and connecting to this terminal here on the starter motor, our big terminal there, and then through the housing of the starter motor itself, this ground cable would be bolted up to the block, and then the electrical energy would go operate the starter motor, millivolts coming back, pushing that current back up the ground cable and back to the battery to complete that circuit. And so our cables are bigger gauge wire. They're often, 3 gauge, 4 gauge, things like that wire. We'll have our positive and negative cables there. Then our starter relay, a relay is like this and it's like this one, and it's really just a high current electrical switch. So I'm going to take this one apart so that you can see how it functions and what it does. So I've drilled out some little pop rivets that were on here so that I can just take this one apart when I choose to. So inside here, what we have is a winding inside here. From here, there's my power in, windings all the way around. Excuse me. Windings all the way around and the ground through the housing right here. And then we've got a little spring and a plunger that's magnetic and a little copper disc. And so what this does is when I get power here, it creates a magnetic field that then turns this whole housing into a magnet, and it'll pull this down into contact, connecting that tower to that tower. And so if I hook this up, there to there, and then I hook my ground just to the housing right here, and then I touch power over to here, then you can see that it pulls into a magnet and pull that guy into contact. And if I don't put my finger there, then it'll jump out and spring it out. So pulls it into contact there. That's no different than what happens for our, I don't know if I'll have enough power or if these are big enough wires. Hopefully it doesn't light this thing on fire, but it should kick my pinion out over here. So if I touch to this tower over here, then you can see it kicks the pinion out. And if I had power on this, then that starter would spin. So it kicks the pinion out there. And so that's all we have going. You can see I just clipped that to the housing to give it a path to ground to get back. But that's the way that your relay works. The relay just connects electrically, but a solenoid, you can see, would connect electrically and also kick the pinion out at the same time. So that's our relay. This is just pulling in and connecting that tower to that tower with this copper disc to get power to the starter motor itself. And so on this design, this is the starter that would go with. There's a terminal here for our power terminal there, that when we get power to that, it also creates a magnet that pulls this down into contact and then kicks the pinion out. So that's what this design would work with, a relay like that. That once they get power through to the starter motor, then it operates the starter motor. The relay is just a high current electrical contact. Versus a solenoid, when you look at what a solenoid does, we have that very same plunger from our relay here. It's just bigger. So that plunger comes in and connects. It's at the back over here and would connect this tower to that tower to get power down to my starter motor. But as that plunger pulls in, it would pivot off of this fulcrum pivot point and kick the pinion out to engage the flywheel or the ring gear on the flywheel at the same time, simultaneously. And so I've got a little cutaway view of a starter motor that I want to put in front of you here. That with this starter motor, we've got the motor inside here, and then we've got our plunger over here with our pivot and fulcrum there, that as we energize on our small wire back here, then that would pull that plunger in, and in doing so would connect that tower to that tower, the two towers together on the back over here, and then at the same time engage the pinion and kick the pinion out to engage the flywheel. And then as we get electrical energy there, then it would operate that starter motor. I'll take a little bit of time to explain the way that a motor works, an electric motor. So we have a couple of rules for electricity. When electricity flows, it generates a magnetic field because it has polarity, right? We have positive charges and negative charges in electricity, just like we do with permanent magnets. And so it creates a magnetic field. And so in that case, with DC systems like what we use what's called the right-hand rule. So if you take your right hand and you go with these three fingers like this, and you put one straight ahead, your thumb going up, and then your middle finger out to the side. Then when current flows in a circuit, then we say that if current is flowing this way with my finger, then the magnetic field wraps around the wire in this direction, and then the force is up. All right? So I don't really care about the magnetic field. So if I just do this, I can say if current's flowing this way, then the force is up. So what we have, this is called an armature, and this is what's inside this electric motor and all electric motors for that matter. This part back here is called a commutator. And what it does is it becomes an electrical contact for power and ground. So we've got the windings through this armature. And so when it connects power and ground, then if power comes in and connects here and current's flowing in this way through this armature, and if current flows this way, then the force is up. And then as it comes around the other way and flows back out through the ground, then the current flow is that way and the force is down. So if I'm up on this side and down on that side, then that would cause this armature to want to rotate. Now, what the commutator does is it maintains that identical polarity the whole time. As every time it rotates to a new set of contacts, then the force is always up on this side and down on that side. So as it rotates, it'll rotate faster and faster and faster and maintain that polarity, force up here, down there, and you cause it to rotate. Obviously, if you reverse the polarity, then it would rotate the other way. So a commutator maintains the polarity on the armature to make sure the force is always up on this side and down on that side. Now, if they make that magnetic field react with other permanent magnets, all right, then they can have opposing fields that then want to cause this to rotate, and that's what they do. They either use permanent magnets to react to the magnetic field of the armature, or they create more electromagnets, which is what this one has, is windings of other wire to react to the armature's magnetic field and allow it to have opposing magnetic fields to make it rotate. So I don't want to leave this slide without pointing out to you again, this is our solenoid, this is our motor and our armature. And so a solenoid does an electrical function in connecting these two terminals here, and then at the same time it does a mechanical function by pushing the pinion out into contact with the flywheel. One of the other things that is on every one of these starter motors is on the front, if this is what all motors look like, then if I put a gear on the front, then it's a motor, right? If I put an impeller on the front, it could be a fuel pump or a water pump, right? If I put a fan on the front, it's a fan, right? So whatever they attach on the end of this determines what type of motor it is. On the end of our starter motors, we have our pinion gear, which this is the end of that there. And so these pinions on the front have another component that's called a one-way roller. And so what that does is, as this comes out and engages and makes contact out here, if the starter is driving the flywheel, it's locked. So in this direction, if I try to rotate this way, it's locked. If I rotate this way, it free spins. And so this one, you can actually hear, this is an old school one, that as it comes out and engages, then in this direction, it's locked. But if I spin it the other way, it free spins. And so that keeps us from overrunning the starter motor. When the starter's driving the engine, we have positive engagement and we're cranking the engine over. But once the engine fires up and it would want to drive the starter, we don't want to overspin the starter and damage it. And so it only allows the force to be transmitted in one direction. So we have little one-way rollers. Both of these are mechanical. If you're in the class, I'd pass them around so you could see the way that they work. But take electrical, you'll get your hands on it. So that's that with our little one-way rollers. So automatic transmissions and manual transmissions will have some sort of a safety switch. They're showing here our neutral safety switch. I'll show you a couple different examples of those. But all that a neutral safety switch really does is it allows us to break this control circuit so that the vehicle couldn't be fired up in gear. So some of them are on the shifter. If you have a console shifter like this, then you'll have your neutral safety switch here that it will only allow you to start the vehicle in park or in neutral. And so this is another one that would be down on the side of the housing of the transmission that allows you to be able to start in park or neutral, and it goes open circuit in drive or reverse. And so that way, if you've ever seen manual transmissions, sometimes people with manual transmissions will bypass their neutral safety switch, and then you go and hit the key and the vehicle will lunge forward because it's in gear. If you haven't experienced this, automatic transmissions would do the same thing if they didn't have a neutral safety switch. And you know it because when you're in drive, if you didn't have your foot on the brake, the vehicle would lurch forward on you anyways. And so it's a safety device to keep that vehicle from being propelled down the road by the starter motor if it was in gear during cranking. And so a neutral safety switch just breaks the control circuit as a safety device to prevent that vehicle from lunging or starting to take off during cranking if the vehicle were to be in gear. So it stops and disengages the control circuit and then ultimately the motor circuit if you tried or attempted to start the vehicle in gear. A simple test for any neutral safety switch is most people will, if you have an automatic transmission, they mostly start their vehicles in park. I know of nobody that gets in their vehicle with an automatic transmission, like shifts it to neutral. Okay, perfect, I'm in neutral, and then starts their car. However, as a test for us as technicians, if it didn't start in park, but it did start in neutral, then I know I have a bad neutral safety switch. So it's a really simple test. It's something you should add to your diagnosis, that if you had a car that did nothing, literally nothing during cranking, you might try throwing it in neutral and then seeing if it starts. If it starts in neutral but it doesn't start in park, you have a bad neutral safety switch. We're much more likely to wear out the park contacts, the park position contacts of the neutral safety switch, because that's where we always start the car from, than you are neutral. So manual transmissions, like I said, will have a clutch switch. They're no different than this neutral safety switch that either connects that wire to that wire or makes an open circuit. A clutch switch does the same thing. For a clutch switch on a manual transmission, you have to push in the clutch to be able to connect that circuit. And so when the clutch is out, it's open circuit. When the clutch is pushed in, it connects the circuit. So then we have our starter motor. Our starter motor is a high current, high torque electric motor. We've looked at a lot of the information on this. We've already looked at our solenoid. We've looked at our little one-way roller, our pinion. This is our armature in here and our commutator. And then these are our magnets here. The magnets that would react with the magnetic field of this armature. High current, high torque. High torque, I forgot to mention it, but you'll notice the pinion gear is small, right, and the ring gear is massive. Anytime you have a small gear turning a big gear, it is a torque scenario. And so when you look at the big gear that's being driven, the bigger that gear is, if you looked at the radius, the diameter is the whole width of that circle. The radius is half of that. The larger the radius, the more turning force you have, right? So if I had a smaller gear like this, it's like having a small pry bar, right? If I had a larger gear like this, that the radius was this long, it's like having a bigger pry bar, right? So the bigger that gear, the bigger that driven gear, the more torque we get from that. And so, or turning force. So on here, this is just a live view of our starter motor and our housing, right? And then you can see your armature and your commutator back here where we would make our electrical contacts for our starter motor itself. So, quick review on this. Our battery is our power source of electrical energy. Our ignition switch allows that driver to control the operation of the starter motor control circuit. Our solenoid and our relay are our high current, high torque, or high current electrical switch. And then solenoids are electromechanical. They do an electrical job plus a mechanical job. And then our relays are just an electrical switch. Our starter motor is a high current, high torque electric motor. So, quick dyad question. When the starting system fails, what symptom will you get? So you get a vehicle or an engine that does not crank over. I want to make sure that you get that type of diagnosis into your head. So if it doesn't crank over, one of the other things on the list that we're going to check is the starting system. And we've talked about the main components in that starting system. So, good enough.